Okay, let's start with the recording. Let me run the program in the backend. So in the explanation, I run program 2 to 3 times, so I clarify the results which we will get in the program. Okay, so I'm just in start. Let me choose number 3. Okay, and 0 battery storage 3 PVs. Okay. The program is chosen with the 500 iterations. Here is the number of iteration. So you can change it to 100, 200, 300. But I will suggest to choose at least 500. More iterations means uh, more number of possibilities while the selection of population. Okay. So let's start with the without DG. Sorry. So in without DG on left side, this is in first column. This is the voltage profile per unit for 14 buses. On right side, in second column, the values are real power in kilowatts. So in without dg.m, these data I will consider later while doing comparison between without dg and with dg. So on left side it's voltage profile per unit, and on right side it's voltage profile. Okay. And how I get the next question, real question, how I get these values. So for that you have to get into the without dg calculation.m file. Okay. So in this file I have just taken line data and load data. So let's explore load data and line data. So in load data file, uh, in first column I have just serial number, and then I have real power at each bus in kilowatts. Then I have reactive power in third column, reactive power in kilowatts for each bus. For example, this means 900 kVAR at bus number 13. Okay, and this parameter is not considered. Okay. So and let me get into the line data file. So in line data file, this is the serial number, this is the from bus, and you can say that from bus to bus, FB to B as nodes. So this will be the first node from 1 to 2, and this will be the 7 node that will be from 3 to 8 bus. So in this way we have around 14 nodes, and we have these nodes. For example, this node starts from bus 2 and ends on bus 5. And next we have resistance in each node in per unit, and this is the reactance in per unit. Okay. So if you want to change your data, or you want to analyze the voltage profile, and then let me get back in again into the without dg calculation. So here I have introduced line and load data, and by these files line and load data are coming into this file without dg calculation. When you will click on when you click on the run button here, then this program, let me break it. Okay, just break it. Okay, so when I'm going to click run on it, then here you can see that I have voltage. So this voltage I just have copy it from here, and then I just paste into the first column here. And for this one, this is the real power loss. I just copied this one. I have just copied this one, and then I paste it to the second column. So this is so now we are done with without dg and without dg calculation.m. Okay, and next there is a per unit calculation, dividing it with the grid capacity, and then conversion of real and reactive powers that were previously in kilowatts, and kVAR conversion from kilowatts into per units. Okay, and next this is the famous forward backward sweep algorithm. There is a complete explanation video that I already shared with you, uh, how this algorithm works. So at the end of this complete program, we have real power, reactive power, and then we have voltage profiles, and at the end we have real power losses, reactive power losses. That's it. Let me run again. Okay, now let me get back into our main program. So up to now we have covered without dg and without dg.m. Now let me explain this file a bit. So this is the solar wind data that we were previously used in, and here we have solar irradiance that is in second column, as solar irradiance is available from 6 a.m. to uh, to 7 p.m. So this is available from 6 a.m. to 7 p.m. And then we have wind data that is available around for 24 hours. And then I already make another video in which I already explain how I get these values for solar and wind data, and I have already provided you stuff how I made the calculation based for the solar calculation. This is the efficiency of the solar panel, and this is the area chosen by our total solar panels, and then some calculation by 24. And this calculation is all about solar and wind data. Okay, so I have paused the video, and now I have continue again, and now let me explain the remaining part. So here is the serial number, solar irradiance, wind speed, and I already provide the reference from where you can get the reference data, and the problem formulation and calculation based on it. It's a separate file, you have to run it, and when you will run this file, then you will get the output at the end. So SW data file, without DG, without DG calculation, these three are files are separate, and PSO file, load flow 1, load flow 2, these are linked with each other. So let me open the main file, which is PSO. Okay, so here is the main file, that is PSO. In PSO file, initially I have to request the number of DGs. So number of the DGs, just for a name, and DG represent here the total number of you can say the total number of PVs and battery storage systems you want to introduce. For example, if you want to choose only 5 PVs without any battery storage system, then you have to put 5 as okay. So if you let me run the program, and so if I want to choose only 3 PVs, I have to just put 3, and then I have to put 0, and then I have to put 3 PVs, and then I have to just run. uh, why I have to choose this, just you can guess the mechanism of flowing. And if you want to choose 3 PVs and 3 battery storage systems, then you have to choose 6 and then 3 and then 3 PVs. So DG will be the sum of uh, how many storage systems and PVs you want to choose, and after that you have to click on enter, and then program will be starts running. Okay, so here I have choose 8,000. It means as uh, you have uh, tell me the requirement that total power will be the 10,000 at max. So I have choose 8,000. Here you can choose 10,000 too. Just I have just changed this to 8,000 just to check the output uh, for the DG's location. Okay. So next here is the decision variables. Variables will be based on how many DGs you want to choose. So if you want to choose 3 DGs, and then this will be the 9. Why 9? 3 will be the 3 will be the reactive powers, and 3 will be the real powers, and 3 will be the locations for DGs. So I'm not talking about now for PVs or storage systems, I'm talking about DGs. So DGs can be storage systems or PVs. So if I want to choose 5 DGs, then this will be the 15. Okay. So 5 will be the real powers, and so there will be the 5 DGs. Okay, and there will be the 5 variables. Okay, and 5 will be the reactive powers, and 5 will be the real powers. So that's why it will be 15. And then this so let me show you. uh, okay, let me click on run button. Okay, so there will be the NVAR. Let me move my cursor there, and there are 18. Okay, okay, and now this section is the problem definition. Here we have to define our problem. So this is the size of the C, and where this calculation is for the battery storage systems, and this will be for the PVs. So in the recent case which we have considered here, we have 3 battery energy storage systems. So let me click on because if we have 0 battery energy storage system, then this part will not be executed. This will not be considered. Only PVs will be considered. So I have choose 3 battery energy storage system. When I click on run, here you can see that number of battery storage systems are 3, which I have choose here. Okay, so we have now programmed this program from 1 to 3, which will be run. Okay, and then let me click on the run. Okay, after that, so this is the minimum location for our battery storage system, which I have choose from 2. This is the minimum lower bound location of the DG as mentioned here, and this is the upper bound location of DG. This is the maximum possible location, and reactive power is chosen to be 0 for battery energy storage system, and real max I have mentioned a lot of parameters. This is the real maximum possible power for our battery storage system, and this you can see that there is 1333.33 uh, because okay, let me click on step. Okay, let me show you. When you pick a variable, then put it just to the command window, click in enter button, and now e raised power 3, and now we have 13 33.3. So these are the kilowatts which are considered now. Okay, let me click on step, and this will be the okay. So let me click on continue here. Okay, so let me show you now the VER minimum. And VER minimum we have, as I already told you, that we have, if we choose, uh, we have three locations for our PVs. Okay, and this will be the uh, maximum. So at the end, from 12 to 15, there is 0.0140. So when you multiply this thing with 1000, then it will be 14. So maximum location will be the 14, 14, and 14. So this is for the PVs. Again, similar things. And let me click red circle here. Let me click on the run program. Okay, so initially we have chosen 6 DGs. So I said initially that we have 6 locations and 6 real powers, 6 reactive powers. So now let me show you. When I move my cursor to any variable, then here at the end you can see that we have six minimum locations. Variable maximum, we have 6 maximum locations that are around 0.0140. Okay, and in the start of program you can see 1.33. Everything will be multiplied by 1000. So this will be the 1333 1333 kilowatts. So these are the minimum and maximum uh, ranges for our variables, for our variables and the data. And you can, here you can also see that there are 6 zeros, so it means we have no reactive power considered. And then maximum iteration considered to be 500. Previously it was 100. You can choose just. So more number of iterations means more number of populations. More populations means more number of possibilities for selection of for more number of iterations means more number of populations. More populations will be more possible values for DG selection. I will show this a bit later. So let's continue. So these are the PSO parameters. Personal coefficient, global learning coefficient, inertia, weight, etc. Okay, and then this is the velocity limits. These are the initialization for. So position will be the DG's location and size, and the cost will be the output which we have considered here, the power losses. And velocity will be the swarms population or particle swarm particle swarms velocity based on the fitness function. And then best position, best position means best possible DG location and size. Best cost means the best possible power losses against the best position. Best position means again best location and best size. Okay, so let me show you now here. So what it means by the particle position here. Let me click on continue. Okay, particle. So now you have to just, you can also trace the values. Just open the particle and then particle. I have just opened the particle workspace. Okay, give it your time. Okay, so here you can see that we have loading. We have 360 swarms, particles. Okay, you can say anything. So we have 360 possibilities. When we have 100, then this will be the less. This will be the around let me show you. when we have okay uh, as when we have this will be the 360s. This will be if we have even six number of DGs, then this will be the 360. But maximum iterations means we have to run this loop 500 times. We have to, this loop will be run for 500 times. In case of 100 we have 360 swarms, but if we are running this at 100 iterations, then we have 100. We have to repeat our outputs 100 times, and in case of 500 we have our program will run the algorithm, repeat the program for 500 times, so more chances with the more number of iterations. So we were here we were at this point, particle I dot position. So what it means, just open this thing, particle, and just move above, and now here you can see 18. So these six, as I explained previously, these will be 0 because we are not dealing with the reactive powers. First six were with the reactive powers, and at the end of this program we have 13 to 18. So these are the locations. So this will be the 4 location. Just round it off. If it is more than 3.5, it will be around 4. This will be the 4, this will be the 12, this will be the 8, this will be the 9, this will be the 2, this will be the 10. So from this thing you can get an idea that nothing is fixed here. The program is so let me click on run again. Run. Let me click this for 3 to 4 times. Okay, so I have done it with 3 to 4 times. Let me open the particle I again. Just close it. Okay, so two values are calculated. Let me open this thing. Okay, so these are all executed. So let me open this position, and still you can see here we have location of 7, 10. It's 7, it's 10, it's 9, and it's 5. Here you can get an idea that these are all the random selection. Nothing is fixed here. So in our random selection we are getting these numbers, and they are performing well. Okay, so particle velocity, and then what is meant by the cost. So when we have these numbers, then we are going into the particle cost. So particle cost means we are getting into the load flow file. Okay, so let me click a red circle here. Okay, when we have a particle number of DG size and location, then we put the data into this cost. So let me see what I have now. So at the moment we have this data. So first six are the real powers, and the last ones are the six locations. So when you will multiply this thing with 1000, then you will get that 1 2 3, this is 9, and this will be the 13, and this will be the 9, this will be the 4, and this will be the 10, and this will be the 5. Okay, just I'm round off, or I'm doing estimate. Let me click on step. So when we have load profile here, then we are getting into the load profile. When I click on step, then we are going into load flow. So make sure if you want to test similar, you have to place red circle here, And after that you again we are okay. So just a minute. Let me run the program again from the start. Okay, so you have to run the program, and after running you have to first click here to place the red circle, then place another red circle here. Okay, now click the program again, choose 6 3 storage systems, 3 PVs. Okay, so at this point we have our input that I previously explained here. You can either open the particle and then open the position. You can choose this thing also. You can copy this variable here and then paste that thing here, and still you have the you can get the same answer. Okay, okay, so now here we six real powers and loss 6 were with the locations for DGs. Just multiply them with 1000 and then round off. And now as the load flow file, we are getting into the load flow file. Now we are into the, now take a look at the DG file. So DG is the still the same file which we have previously as the particle positions previously, and now we are into the load flow file and we have the DG with same name, with different name but same values. So it means that we are getting our input from here, and after getting our input from particle song optimization, we are putting that input into our objective function, and the load flow will calculate the fitness, the cost for our objective function. So after getting into the load flow file, and now we have to place our DGs at specific locations, as we can read our data from this file. So after getting into this, let me click on continue button. The above few lines, these are defining the values parameters for per unit calculation and per unit values for resistance reactance, and this is the part where we are putting our battery energy storage systems and PVs at a specific location. So from the DG we can understand that at okay, okay, so let me show you PG here and QG. So now let me show you. Okay, here you can see that I have nothing in PG and nothing in QG. So both these variables are empty, and after performing these lines, we will put our PGs, because in this case which we have choose, we have nothing in our QG, and in our real powers PG we have these certain 6 numbers. So let's try it. Okay, so here both these are defining the PS and QS. Let me run the program here, click on continue, and now I have executed this part. And after part, let me again show you the PG. And here you can see that first, second, third and fourth, our battery energy storage systems and PVs. These two are battery energy storage systems, and the next two are the PVs. So we have put our uh, DGs at their specific locations. So from this thing, you can get an idea that DG endpoints are representing their locations, and DG first six numbers are representing the real powers. And after that we have per unit calculations, and then we have again the whole process for the load flow analysis. So let me run the program up to this point. After that, so here we have P loss at each point. After sum up, the losses are actually around 480. So now let me click on end, click on step. Okay, so now at this point we have, when I click on step, let me show you what I have for the cost now. So this is the 480. So this was the value which I have uh, executed previously. So the conclusion is, against this combination, or against this combination of DG size and locations, we get our fitness function, we get our uh, cost is around 480s. And then this process will be repeated for whole iterations, and after that it will finds the best possible locations and sizes for the DG. Okay, okay, now let's get back to the particle I cost, and then this is the personal best calculation. Okay, and this is the global best calculation, and if our personal best is better than if our personal best is better than the global best, then this will be the replaced. So let me click on this step button. So here let me show you particle I best cost. Open the particle and then open the best. Initially it put the first outcome which is received into the particle I best. So initially we have 480.80, 8190, and exactly the same is stored here. And in position we have the combination. Later on this combination will be represented as the best location and sizes. Okay, now let me run this program again. Okay, so initially this becomes true. Okay, now, okay, now again this will be the second. Now again this will be the second combination, and now particular position will be. So now for this time we have different locations and different sizes for DGs. Let me click on step button, click on the cost. Let's skip this for a while. Let me show you the cost. This time we have better cost, and now we have algorithm will update the best. Okay, let me open the particle best, I have best 447. This will be updated as the best value. So in this way, the PSO optimization algorithm is updating the best possible locations and size combination. And then we are going into the main loop. Velocity parameters are initially velocity parameters are chosen to be 0, and then velocity limits update position. Okay, velocity mirror effect apply position limits, and then update personal best. And again for evaluation, based on update position, apply velocity limits, apply mirror effects. These all effects on the particle position, and based on the particle position, we have different locations and uh, size variation for our case. I mean, based on these limits and updates, our particle eye position, that is actually the input for our objective function, will be updated by these factors, and then this update will be get into the load flow file, and after that load flow file will calculate the power losses, and then we will put that as the particle eye cost. And then we have to compare the particle eye cost with the values parameters we already stored in, and then we have update global best. Okay, and then this will be the represent the best possible cost against each iteration, because for a iteration, if we find a solution, then for next iteration, based on the update velocity limits, update position, velocity mirror effect, next time it finds a solution, it finds the uh, variation which is possible, and create less cost. And after that, we in our global best, we have the combination of, uh, as I explained previously in our particle, uh, these are all forms will be filled up, and after that we have positions for each swarm, cost for each swarm, as you can see here. Third one was the best, and second one was the worst. Similarly, we have almost each table have a certain number. Okay, so actually program is stopped in the background. Okay, so I was in that point. Yes, in each table we have different combinations, and for each parameters, some are the best values and some are still the worst values. So based on, okay, so let me explain again how the PSO algorithm finds global best. So previously I explained you that we have total number of population that are defined here. Here we have number of populations. If we have number of DGs, in this case we have 6 DGs, multiply this thing with 60, it will be 360 population swarms. And if we have 100 iterations, then 100 times 6 populations will be executed. For example, for one iteration, 600 populations swarms finds their best value. And for example, this is all these values were executed, calculated against one iteration, and in next iteration all these 360 values will be updated. So here we have best values, worst values, and what will be the global best. So in this iteration, for example, this is the iteration number 100, as the program is completed its evaluation. So it's 100 iteration, and in this case 100 iteration, we have the best and worst values. So what will be the global best? Let me open this thing. We have 271.1215 will be our global best. Okay, 1217 and 1215. Point 1215, point 1213. Okay, so at this point, let's see. Now it's become 1213. So as the program progress, and it is 12. So previously there was 1209. So as the problem progress, it finds its best possible solution. So against this thing, for example, this is the best. So let's open this variable. So this is the combination of this size, and this is the Lukaian combination for 6 DGs. So first three will be the for battery energy storage system, and next three for the PVs. As I previously explained in the start, that the first outcomes or initial problem definition is about battery storage system, and the next ones are about PVs. So if we are choosing only PVs, then only these numbers will be for PVs. Okay. So after finding the global best, now let me show what is global best here. Just copy this thing and then paste it here. Click enter. Okay. It says it's cost. What is cost actually here? Cost is the real power. So let me. But there is a global best. Let me open it from here. Global best, this is the global best struct, and then you have to open the, this is the cost and this is the position. So in position we have that combination stored here. These are the real powers, and next are the sizes. Okay, and then there is a plot, then there is a now at this point we are putting our best location and size from here previously, which we calculated through load flow 1 file. Now we have best size and location of DGs. Now we are putting these data into load flow 2 file. Okay, let me click on continue. This is the convergence curve iteration convergence curve based on these iteration numbers. Now we are switching into the load flow file 2, and now let me click on PSO, click on step. Okay, now we are into it. So now at this point DG we have same result which I show you previously. So DG is the same number, same size, same location. So from here you can get an idea that we have the optimal location is 986979. Your question is that why our numbers are repeating. The answer is simple, that we have total 14 number of buses, and we have just uh, possible variation is from 2 to 14, so more chances of repeating number here. So if you want to choose 3 digits, then less chances will be for the repetition of location. Location is repeated because first of all we are putting PV and battery storage system to the same location, and second we have less number of variation possible. So try with uh, three number of digits, then results will be fine. So after that it's putting digits still again at this point. Let me previously I think so I have not explained this part. Let me explain now this part. Okay, so let me first show you the DG here. Just type DG here. Okay, so we have 986,979. So first of all let me show you what is step. Okay, at this point PS is not defined. Now let's see what is PS. PS is the first outcome, this one. Okay, and QS will be this one. As we have a number of digits are 6, so for one iteration uh, for this line, or when n equals to 1 for this line, means this number. When n equals to 2, and let me click again, sorry, it's executed. For when the okay, when we have n equals to 2, and when we have just a moment, when n equals to 2, then this line means we have second number. When n equals to 3, then this line means we are directing to 3. When n equals to 4, and this line will become 0 because 1 2 3 4. And what this means that at which point we have to put our PG when n equals to 1, and this means this power we have to put at location 9. And when n equals to 2, this will be 0, this will be 0. Okay, we have to put 0 when n equals to 1, we have to put 0 at location 9 as reactive power, because we have location same. And if you want to change reactive powers will be introduced here. For example, I have n equals to 5, and at this point at 5, this will be the 5. So this will be the generation power of DGs. This is the fifth possible number, and this will be updated to the this will be put on the location number 7. So anyway, at the end of this program, this will calculate the power and real and reactive powers. And let me get back to it. Okay, after now calculating PL and QL, real and reactive powers, then these numbers are calculated by doing without DG calculation by this problem. uh, MATLAB code, these numbers are calculated, and then I have to compare it with the PL and QL which I get from the load flow profile. And after that, here is the location and size calculation for battery energy storage system. Again, here is the rest of the program. So your main concern was about this is the voltage profile at each bus, and this is the real power at each bus. Your main concern was actually about the location repetition. So as I explained before, then if you want to choose more number of DGs, more number of uh, around 4 to 5, then more chances of repetition. But if you want to choose 3 2 1, then there will be less chances, because we have a small network. 2 to 14 is a very is not a much bigger network, just like 33 or just like 69. So that's it. If anything, if any part is remaining, you can still tell me. I will uh, you can put your concern on the chat, and then I will respond there. Okay, thanks for watching.